Welcome to Graph Theory Lecture 25. Today we're going to explore various applications of Hall's marriage theorem. And again, I haven't proved this theorem yet, and I will not today. This will be the stuff of tomorrow's lecture. So as a reminder, here is Hall's marriage theorem, which we abbreviate the HMT. It says that if you have a bipartite graph, GXY, so G is the graph, X is the left vertices and Y is the right vertices. And each subset of left vertices has at least as many neighbors altogether. So the number of vertices that have at least one neighbor in the subset, that number is at least equal to the size of the subset. This is called the Hall condition. If this is satisfied, then G has an X-complete matching. So matching in which each vertex in X is matched. So each left vertex is matched. So, and as I said, we won't prove this now, but we will give several more applications. I think it's worth appreciating the theorem first before proving it. And this is best done by seeing what else follows from it. So here is one, or actually two applications which involve systems of representatives. This is not about graphs, but really it's about graphs secretly. So let me state this. There, in a sense, this is an equivalent form of the theorem. And this form has an advantage. I'm not sure if it's an actual advantage, but it certainly makes it popular, that it never mentions graphs. So when non-combinatorialists use the Hall marriage theorem, they often use it in one of these two forms. Here is the first one. This is known as the existence of systems of distinct representatives. Let A1 ... AN be any n sets. Assume that the union of any P of the sets has size at least P for all P between 0 and n. So in other words, let me make this rigorous. Assume that the union of AI1, AI2, ... AIP is at least P for any I1 less than I2, ... less than ... less than IP less or equal to n. Then we can find n distinct elements, one from the first set, one from the second set, one from the third set, and so on, and ultimately one from the last set. So, and what is SDR? Well, an n-tuple A1 ... AN of n distinct elements like this is called a system of distinct representatives for our n sets A1 up to AN. The name is fairly natural. We're basically choosing representatives from each of the sets and making sure that these representatives are distinct. So here is an example. Take a standard deck of cards and deal them out into 13 piles of 4 cards each. Randomly, it doesn't have to be 4 cards of the same rank. Then, using the theorem we just stated, we can see that it is possible to select exactly 1 card from each pile, so that the 13 selected cards contain exactly 1 card from each rank. So exactly 1 ace, exactly 1 2, exactly 1 3, ... and so on. Indeed, this follows from the theorem applied to AI equals the ranks that occur in the ice pile. it is easy to see that if you combine p piles, altogether they contain at least p different ranks, usually a lot more, but in the worst case scenario, it's like there is only 4 cards of each rank, and there is 4 p cards in those p piles. So you cannot have fewer than p different ranks there. So you can pick one rank in pile 1, one rank in pile 2, and so on, such that all those ranks are distinct, which means, of course, that you have representatives of all ranks. Okay, so proof of the theorem. First, we assume without loss of generality that all n sets a1 dot an are finite. How do we ensure that? Well, we can just replace each infinite one by an n element subset. And it's not hard to see that this does not break this condition. So if we do this, we get finite sets, but they still satisfy this assumption. So the assumption here will not be disturbed by this change. Make sure you so check this. Okay, furthermore, without loss of generality, we assume that no integer belongs to any of these n sets a1 dot an. Otherwise, we just rename the elements of the sets so that they aren't integers anymore. This is a very stupid thing, but it's necessary in order to make sure that our graph later will not have accidentally equal vertices. Now, let x be the set of integers from 1 up to n, and let y be the union of all our n sets. We just made sure that this is a finite set. So these are both finite. And let's define a simple graph G as follows. The vertices of G are the elements of X union Y. And this graph is going to be bipartite, with X being the left vertices and Y being the right vertices. Now, as for the edges, a vertex in X is adjacent to a vertex in Y if and only if the vertex in Y belongs in the set corresponding to the vertex in X. So the adjacencies encode which elements of this union are in which AI set. And there are no further adjacencies. In particular, no 2 vertices in X are adjacent to each other, and no 2 vertices in Y are adjacent to each other. So this is actually a bipartite graph. Furthermore, the assumption here ensures that it satisfies the whole condition. This is something you should check. So wait, I'm waiting 10 seconds in which you should really check that this is a whole condition. Right, so by the whole marriage theorem, we conclude that this graph G has an X-complete matching. And this matching, so what is X-complete? X-complete means that each edge, each vertex in X is matched to something. And of course, its partner has to be a vertex in Y, because it's bipartite. So here is its form. Each vertex in X has a partner in Y. One more, so I'm again using the fact that this graph is bipartite, so you cannot have any further edges because each edge needs at least one vertex in X. So if it's X complete, you cannot, it has only n many edges, not more. Okay, so these elements A1 up to AN in Y are precisely the n distinct elements we are looking for. Well, because they are distinct, otherwise our matching would have 2 edges with the same endpoint, which is not what a matching can do. And furthermore, for each I, we have AI is in capital AI because the vertex AI is adjacent to I in our graph. So this proves the theorem. And conversely, it is not hard to derive the whole marriage theorem from the above theorem. So this is not just a consequence, this is actually an equivalent form, but you can do it on your own. It's not something we need to do. So this was the first set theoretical restatement of Hall's marriage theorem. And here is another, which is probably less useful, but I feel like I should state it nevertheless. This was systems of distinct representatives. So basically we have n sets and you want to choose a representative from each that are distinct. This one will be this existence of systems of common representatives. So you have n sets and you have another n sets, and you want to pick these representatives of the former n sets that are also representatives of the other n sets. This time we can no longer require them to be distinct. So here is a statement. Let A1 up to AN be n sets. Let B1 up to BM sets. We are not even requiring the same number. Assume that for any choice of numbers I1 less than I2 ... less than IP less or equal to n, there exist at least p elements J such that the union AI1 union AI2 and so on union AIP has non-empty intersection with Pj. Then there exists an injective map sigma from 1 up to n to 1 up to m such that all i's satisfy AI intersect P sigma I is non-empty. So what is the claim is saying that you can match up each set here with some set here so that they have non-empty intersection. And injective means that no two different sets here get matched with the same set here. Otherwise it would be too easy. And this condition is basically, again, this is a condition that's pretty obviously necessary. The interesting part is that it's efficient. Okay, and the proof is, I'm leaving this to you. Again, it is, so again, construct an appropriate bipartite graph and apply Hall's marriage theorem. So much for this set theoretical versions.